Before we begin, I want you to find a comfortable position. Sit back or lie down, let your shoulders drop, unclench your jaw, take a deep breath in and let it out. Imagine for a moment that you are floating. You are far away from the noise of the city, far away from the emails and the traffic. Sucks. You are drifting in the deep velvet blackness of space. Here there is no wind, there is no sound. There is only a profound, heavy silence. It is a silence that has existed for billions of years. In this place, the Earth is just a small blue marble in the distance. It looks fragile. It looks safe. But out here in the dark, things are moving. Things that do not care about our safety. Today I want to tell you a story about the day that silence was broken. It begins on the 24th of October in the year 2025. On Earth it was a Tuesday. People were drinking coffee, rushing to work and scrolling through their phones. The news was talking about politics and the weather. But high above the atmosphere in the quiet observatories on top of mountains and in the silent data centers of space agencies, a small group of people were holding their breath. They were watching something new. They called it 3-Eye Atlas. In the language of astronomers, the name told you exactly what it was. The number 3 meant it was the third of its kind we had ever seen. The letter I stood for interstellar. This object did not belong to our solar system. It was not an asteroid from the belt between Mars and Jupiter. It was a visitor. It had travelled through the emptiness of deep space for thousands, maybe millions of years just to pass by us. Atlas was strange. It was not round like a planet, and it was not a messy cloud like a comet. It was long and thin, tumbling end over end through the dark. It moved with incredible speed, 87 kilometers per second. At that speed, you could travel from New York to London in less than 1 minute. Because of this speed, we knew it was not staying. It was just passing through. It was going to dive toward the sun, loop around it, using gravity like a slingshot, and then shoot back out into the darkness, never to return. Or at least that was the plan. That was what the laws of physics said should happen. Isaac Newton wrote down these laws over 300 years ago, and they had never been wrong. If you know the speed of a rock and the mass of the sun, you know exactly where the rock will go. It is simple clockwork. But Atlas had a surprise for us. As Atlas raced toward the center of our solar system, it approached a moment that astronomers call solar conjunction. This is a very important concept, so let's visualize it. Imagine you are standing in a dark field looking at a friend who is holding a flashlight. You can see them clearly. But now imagine a giant searchlight turns on right between you and your friend. The light is blinding. You can no longer see your friend. You cannot see their hand signals. You cannot hear them if they shout. The light drowns out everything. That is solar conjunction. From the perspective of Earth, Atlas was moving behind the sun. The sun is a massive ball of burning gas, and it is incredibly noisy in terms of radio waves and radiation. When an object goes behind the sun, or even close to it, we become blind. Our telescopes cannot look at it because the glare would destroy them. Our radar signals cannot reach it because the sun's interference swallows them up. For exactly 8 days, Atlas would be invisible. 8 days of silence, 8 days of waiting. The scientists were not worried. They had the math. They calculated the trajectory down to the millimeter. They knew exactly where Atlas would enter the shadow, and they knew exactly where and when it would come out. They programmed the telescopes to wait for it on the other side. It was routine. It was just math. On the 24th of October, Atlas slipped into the glare of the sun. The signal on the screens went flat. The connection was lost. The object was now alone in the fire. 1 day passed, then 2, then the 5. In the control rooms, people drank coffee and waited. They simulated the path over and over again. In their minds, they could see the great rock swinging around the star, fighting the heat turning the corner to come back to us. Day 8 arrived. The telescopes turned to the specific point in the black sky where Atlas was supposed to appear. The cameras opened their shutters. The computers waited to catch the reflection of sunlight off the object's surface. Minutes passed. The point in the sky remained empty. The astronomers checked their clocks. Maybe they were a few seconds off. They widened the search area. They looked a little to the left, a little to the right. Nothing, just the empty stars. A cold feeling began to spread in the room. It was the feeling of a fundamental truth breaking apart. Rocks do not disappear. Gravity does not make mistakes. Then a voice called out from a station in the back of the room. "I have it," the voice said, "but the position is wrong." They threw the image onto the main screen. There was Atlas, but it was not where it was supposed to be. It was far too close. During those 8 days, while it was hidden in the blinding light of the sun, something impossible had happened. Atlas had changed its path. It had not just swung around the sun, it had accelerated. It had pushed itself. To be in this new position, Atlas must have increased its speed by 4,000 kilometers per hour while it was inside the blind spot. Natural objects cannot do this. A rock cannot decide to go faster. A comet can sometimes speed up if ice on its surface melts and shoots out gas like a small rocket engine. But Atlas was dry, it had no ice, it had no tail, there was no gas cloud around it. It had simply decided to move. The room went silent. This was a different kind of silence than the one in space. This was the silence of fear. We rely on the laws of physics. They are the foundation of our reality. We trust that the sun will rise, that apples will fall down, and that planets will stay in their orbits. When we look at the sky, we see a giant machine. It is beautiful, but it is predictable. But on that day behind the curtain of the sun, the machine had broken. Or perhaps someone was driving it. Think about the terrifying beauty of that idea. For 8 days, while the entire human race was blind to it, this visitor did something in the dark. It waited until we could not see it. It used the shadow of the sun, the only place where we could not watch, to change its course. Why did it turn? Where was it going now? The new trajectory was calculated quickly. The computers drew a red line across the screen. Before the turn, Atlas was heading back out to the deep stars away from us. Now the red line was pointing inward. It was not leaving the solar system anymore. The new path was a perfect intercept course. It was coming toward Earth. In that moment, the vastness of the universe felt very heavy. We like to think we are important. We like to think we are the masters of our domain. But when you stand next to the mechanics of celestial bodies, when you see a mountain of rock moving at 80 kilometers per second, changing direction like a fighter jet, you realize the truth. We are small, we are very, very small. And something massive, something that knows how to hide in the light, is coming to meet us. To understand why an anomaly in space is so terrifying, one must first understand the absolute rigidity of the rules that govern the cosmos. In the vast, silent cathedral of the solar system, nothing moves at random. Every rock, every speck of dust, and every giant planet follows a path that was determined the moment it was captured by the sun's gravity. This is not a chaotic environment. It is a clockwork mechanism of terrifying precision. When astronomers look at the sky, they are not just seeing where an object is right now, they are seeing where it was, and more importantly, where it will be. This is the magic of orbital mechanics. To track these movements, the scientific community relies on a system known as JPL horizons. Managed by the Jet Propulsion Laboratory, this is essentially the cosmic address book for the solar system. It contains the precise trajectory data for hundreds of thousands of asteroids, comets, planets, and moons. The logic behind JPL horizons is rooted in the laws laid down by Isaac Newton and Johannes Kepler centuries ago. Imagine gravity not as a force that reaches out and grabs you, but as a shape. The sun is a heavy ball sitting in the middle of a stretched sheet of fabric which represents space-time. It creates a deep dip or a well in the fabric. When an object like a comet enters the solar system, it is rolling along the edge of this curved fabric. If the object is moving slowly, it rolls down into the hole and crashes into the sun. If it is moving incredibly fast, it might just dip slightly before shooting back out into deep space in a straight line. But if the speed and the angle are just right, the object gets trapped in the curve. It constantly falls toward the sun, but misses it because it has enough sideways momentum. This eternal state of falling but missing is what we call an orbit. JPL Horizons works by taking 3 or 4 observations of an object over a few nights. By measuring exactly where the point of light is against the background stars, computers can calculate the entire curve. It is like seeing a small segment of a drawn circle and being able to predict exactly how big the rest of the circle is. For a standard object, this prediction is flawless. You tell the computer the object's position and speed today, and the laws of gravity, which are constant and unchanging, will tell you exactly where it will be in 10 years. It is a closed loop. The energy remains constant. As a comet falls closer to the sun, it trades height for speed, accelerating as it dives in. As it swings around and moves away, it trades that speed back for height slowing down. This is the ballistic trajectory. It is the path of a stone thrown by a giant. The stone has no engine. It has no will. It goes exactly where gravity tells it to go. When we look at the data in JPL Horizons, we are looking for this smoothness. We are looking for a curve that fits the equation perfectly. When the real-world observation matches the computer prediction, the universe feels safe and understandable. It means the rock is just a rock, drifting through the dark, obeying the ancient laws of mass and motion. But then there are times when the dot on the screen does not match the prediction. The telescope looks at the coordinates where the rock should be and finds empty space. The rock has arrived early, or perhaps it is running late. This is the first whisper that something is wrong. This is the first hint that the stone might not just be a stone. The mystery. The Oberth effect. If gravity is the sheet music of the cosmos, the Oberth effect is the virtuoso solo. It is a concept in physics that is counterintuitive, elegant, and incredibly powerful. It explains why if you want to change your orbit or gain speed, the best place to do it is not when you're floating slowly in deep space, but when you're falling fastest right next to the sun. To understand this, imagine you are on a playground swing. If you want to go higher, you do not pump your legs when you are at the very top of the arc where you are momentarily stopped in midair. Pumping your legs there does almost nothing. Instead, you wait until you are swooping down right at the bottom of the swing, moving at your maximum speed. That is the moment you kick. A small push at the bottom translates into a massive increase in height on the next swing. This is the Oberth effect. In the language of physics, kinetic energy, the energy of motion is related to the square of your velocity. This means that energy grows exponentially as you get faster. Adding a small amount of speed when you are already moving very fast generates far more mechanical energy than adding that same amount of speed when you are moving slowly. When a spacecraft or an anomalous object approaches the sun, it falls into the gravity well we discussed earlier. As it gets closer to the sun, known as the perihelion, it is screaming through space at its maximum velocity to fight the sun's pull. If an object wanted to leave the solar system or change its path significantly to visit a specific planet, the cheapest way to do it in terms of energy is to apply a push exactly at that closest point. A rocket burn that would give you very little change in the outer solar system will give you a massive change if performed at perihelion. This is why we call it an art rather than a random occurrence. In nature, randomness is usually inefficient. A rock tumbling through space does not care about efficiency. If a comet heats up and shoots out a jet of gas outgassing, it happens randomly, usually when the sun warms a specific patch of ice. It is messy. It is chaotic. It happens at irregular intervals. However, if you see an object change its velocity sharply and precisely at the exact moment of its closest approach to the sun, you are looking at optimization. You are looking at a maneuver that maximizes the laws of physics. It is the difference between a leaf blowing in the wind and a hawk diving for prey. The leaf goes where the wind takes it. The hawk uses gravity and aerodynamics to gain speed, then angles its wings at the perfect moment to swoop up. When we analyze the trajectory of a suspicious object, we look for this specific signature. Did the deviation happen gradually like a slow leak? Or did it happen right at the bottom of the gravity well where a pilot or a computer system would know? It provides the most power. The Oberth effect implies a knowledge of the environment. It implies a utilization of the sun not just as a heavy object to orbit around, but as a gravitational slingshot to be used for propulsion. Comparison. Recalling the Oumuamua event of 2017. The haunting story of Oumuamua, the first interstellar visitor detected passing through our solar system in 2017, serves as the perfect case study for this distinction. It was a messenger from the dark between the stars, and it refused to behave like a normal rock. When Oumuamua was first spotted, astronomers assumed it was a comet. Comets are common. They are dirty snowballs that fall in from the cold edges of the system. As they get close to the sun, the ice melts, creating a fuzzy cloud called a coma and a long, beautiful tail. This melting process acts like a natural rocket engine. The gas shoots out one way and the comet is pushed the other way. This is a non-gravitational acceleration, but it is natural and expected. However, Oumuamua was different. Deep telescope images showed it was a point of light, not a fuzzy cloud. It had no tail, it had no coma. It appeared to be a solid object likely made of rock or metal, possibly shaped like a long cigar or a flat pancake. By all traditional definitions, it should have been an asteroid, a dead dry rock. And yet it moved. As Oumuamua passed the sun and began its exit journey back into the darkness, it accelerated. It did not slow down as much as gravity said it should. It was being pushed. If it was a comet, the outgassing would explain the push, but there was no gas to be seen. If it was an asteroid, there should be no push at all. This brought the scientific community to the stark difference between drifting and being driven. Drifting is passive. A piece of driftwood floating in the ocean moves with the current. If the current swirls, the wood swirls. Its orientation, which way it faces, is random. It tumbles. Oumuamua was indeed tumbling, spinning in a complex way. This supported the natural theory. Perhaps it was just a weird rock with invisible gas jets. But being driven or steered implies a force that contradicts the natural flow. Imagine seeing a boat in the ocean. It is bobbing up and down looking like debris. But then you notice it is moving cross-current. It is fighting the flow of the water. Even if you cannot see the engine, the motion betrays it. With Oumuamua, the deviation was small, but it was undeniable. The object was pushed away from the sun with a force that declined smoothly as it moved away. Some scientists proposed it was a solar sail, a piece of technology that uses the pressure of sunlight itself rather than rocket fuel to push it along. Sunlight hits the large surface area of the sail, imparting a tiny but continuous force. If it was a solar sail, the tumbling might have been a broken mechanism, a piece of ancient wreckage caught in a spin. Or perhaps the tumbling was intentional, a way to scan the environment in all directions. The crucial comparison lies in the data residuals. When you fit a drift model to the data, the lines do not match. There is a gap. When you fit a driven model, adding a constant push from the sun, the lines snap into place perfectly. The difference between a rock and a ship is often just a decimal point in a velocity equation. A rock submits to gravity. A ship negotiates with it. Oumuamua negotiated. Expansion. The feeling of wrong numbers and the energy of mountains. There is a specific kind of quiet that falls over a control room when the numbers stop making sense. It is not the panic of a movie scene with alarms blaring, it is a cognitive dissonance. You're looking at a spreadsheet or a graph and your brain tries to reject what it sees. You trust the laws of physics more than you trust your own eyes, so the first reaction is always, I made a mistake. You check the calibration of the telescope. You check the atmospheric distortion codes. You check the timestamps. You assume the error is in the machine or in the human because the universe does not make errors. But when the error persists, when the deviation remains stubborn and consistent across multiple observatories, a different feeling takes over. It is a creeping realization of scale. Let us talk about the energy involved here. It is easy to look at a dot on a screen and forget what it represents. We are discussing an object the size of a mountain. Imagine the island of Manhattan carved out of rock and ice floating in the void. This is billions of tons of mass. To change the velocity of a pebble by 1 kilometer per second requires very little energy. You could do it with a slingshot. To change the velocity of a car by that amount requires a massive tank of chemical fuel. But to change the trajectory of a Manhattan-sized object, to deviate a mountain from the path gravity has chosen for it, the energy requirements are astronomical. We are not talking about the fuel in a rocket tank, we are talking about energy comparable to the total nuclear arsenal of nations, or the output of a large power plant running continuously for years, all released in a controlled, sustained manner. In physics, kinetic energy is equal to 1/2 times the mass times the velocity squared. Because the mass of a comet or large asteroid is so incredibly high, often measured in the trillions of kilograms, even a tiny change in speed requires a staggering input of joules energy. If the object is natural, this energy comes from the sun boiling off millions of tons of ice in a violent, chaotic eruption. It is a brute force explosion. But if the object is artificial, if that deviation is steered, then you have to imagine the engine capable of generating that force, though. You have to imagine a propulsion system that can gently push a mountain without shattering it. It implies a mastery of energy generation that is far beyond human capability. It implies a power source that does not run out or a method of propulsion that harvests the energy of the vacuum or the stars themselves. Looking at those deviant numbers, you are not just looking at math. You are looking at the footprint of a giant. You are seeing the wake left behind by something that has the power to ignore the sun's command. The numbers tell you that something heavy refused to fall where it was supposed to fall. It is a humbling and terrifying realization. It turns the cold vacuum of space into a place of hidden activity. It makes you realize that while we play with firecrackers on Earth, there may be engines moving mountains in the dark, operating on a scale of energy that we can barely comprehend. The deviation in the data is the only smoke signal we have hinting at a fire burning somewhere in the deep cold night. To truly understand why Oumuamua remains such a frustrating puzzle for astronomers, we must look beyond its movement and focus on its material. How do we know what an object is made of when it is millions of kilometers away? We cannot send a geologist to hammer off a sample. We cannot catch it and put it under a microscope. In the vastness of space, we have only one tool: light. This brings us to the science of spectroscopy, which is essentially the art of reading the rainbow. Think of the light reflecting off an object not just as brightness, but as a carrier of dense information. When astronomers capture light in their telescope, they pass it through a prism. This prism breaks the light down into a spectrum of colours from violet to red. If you were to look at a perfect light source, you would see a solid band of colours, But when we look at objects in the universe that rainbow is not perfect, it is full of holes. There are tiny dark lines like missing teeth or gaps in a fence appearing at very specific spots in the rainbow. These are called absorption lines. Every element in the periodic table, hydrogen, helium, carbon, iron, has a unique appetite. It likes to eat very specific colours of light. For example, hydrogen might absorb a specific shade of red. Sodium might absorb a specific shade of yellow. By looking at which colours are missing from the spectrum of Oumuamua, scientists can read its chemical barcode. It is similar to scanning an item at a supermarket. The barcode tells you instantly if you're looking at a bag of apples or a bottle of water. When telescopes turned their gaze toward Oumuamua, they tried to read this barcode. They were hoping to find the clear signature of water ice, which would prove it was a comet, or the signature of silicate rock, which would prove it was an asteroid. What they found instead was ambiguous and fascinating. The surface was dark and reddish. In our own solar system, a deep red colour usually tells a story of age. It suggests the presence of organic materials, complex compounds based on carbon, that have been exposed to the harsh radiation of deep space for a very long time. Astronomers call this material tholins. It is like a layer of cosmic sunburn or the crust on a piece of burnt toast. This spectral reading suggested that Oumuamua had been travelling through the void between stars for millions, perhaps billions of years, slowly cooked by cosmic rays, until its surface turned a deep dark red. But spectroscopy is only skin deep. It tells us about the paint, not the engine. It tells us about the crust, not the core. To understand the true anomaly, we have to dig deeper into the physics of the material itself. The cosmic kitchen. How elements are born. To understand why the potential metallic nature of Oumuamua is so controversial, we need to take a step back and look at the history of matter itself. We need to talk about nucleosynthesis. This is the story of how the universe cooks. Imagine a star not just as a ball of fire, but as a giant spherical pressure cooker. In the beginning, shortly after the Big Bang, the universe was simple. It was a soup made almost entirely of the lightest gas, hydrogen. Inside the core of a star, gravity is so intense that it crushes hydrogen atoms together. It squeezes them until they smash into one another and fuse. This process is called nuclear fusion. This fusion releases the massive amounts of energy that make the star shine. When hydrogen fuses, it creates helium. As a star gets older and runs out of hydrogen fuel, it begins to squeeze the helium. This creates heavier elements, carbon and oxygen. This is the ash of the star's fire. If the star is massive enough, it keeps squeezing harder and harder. It fuses carbon into neon, then magnesium, then silicon. It is a chain reaction, building heavier and heavier atoms layer by layer like an onion. But this process hits a wall. That wall is iron. Fusing light elements together releases energy, which pushes against gravity and keeps the star alive. But fusing iron is different. Fusing iron consumes energy. It is a dead end. Once a massive star builds up a core of iron and nickel, the engine stops. Gravity wins. The star collapses in on itself in a split second and then explodes in a catastrophic event called a supernova. Here is the important takeaway. Nature creates heavy metals like iron and nickel only in the chaotic, violent heart of dying stars. When the star explodes, it sprays these metals out into the universe like a dirty aerosol can. These metals mix with gas dust, ice and rock. They clump together in the cold dark to form nebulas and eventually new solar systems. This is why in nature we rarely find a giant pure block of refined metal. We find ore. We find iron mixed with rock, mixed with oxygen, mixed with dirt. Nature is messy. It makes fruitcakes, not distinct, separate slices of ingredients. The anomaly of iron and nickel. This background brings us back to the specific strangeness of Oumuamua. If Oumuamua were a natural rock, it should be a messy mix of things. If it were a typical comet, it should be a messy ball of ice and dust held together loosely by weak gravity. However, there is a strong argument often discussed by proponents of the artificial hypothesis that focuses on the structural integrity of the object. Oumuamua was not floating gently, it was tumbling. As it spun through space, its brightness changed dramatically. At its brightest, it was 10 times brighter than at its dimmest. To explain this extreme flashing, the object had to be extremely distorted in shape. It had to be either very long and thin like a cigar or very flat and wide like a pancake. Here is the problem: centrifugal force. Imagine you have a long, thin stick made of loose gravel and ice, which is what a comet is. If you spin that stick around quickly, the ends will feel a force pulling them outward. If the material is weak, the stick will break apart. It will disintegrate into a cloud of dust. Calculations showed that for Oumuamua to spin as fast as it did while being as long or flat as it was, it needed to be made of something strong. It needed high tensile strength. It could not be a loose pile of rubble. It had to be solid. This leads some scientists to consider the density of metals. Iron and nickel are common in the universe. We do have iron meteorites that fall to Earth. These are basically chunks of dead planet cores that were smashed apart billions of years ago. They are heavy, dense and metallic, but a natural iron meteorite is a lump. It is jagged, irregular and thick. The artificial alloy hypothesis suggests something different. If Oumuamua was a light sail, a thin reflective sheet used for propulsion, it would need to be incredibly strong, incredibly thin and highly reflective. In our human industry, when we want something strong and shiny that does not rust or break in space, we do not use raw iron. We make steel. We mix iron with a little bit of carbon. To make it stainless, we add chromium and nickel. We refine it. We remove the impurities. We roll it into flat sheets. Finding a block of raw iron in space is rare but natural. Finding a thin, flat sheet of material that behaves like a perfect reflector is a different story. That is not alchemy, that is engineering. The anomaly here is the combination of shape and material. Nature does not typically roll metal into thin sheets. Nature tends to make spheres or jagged potatoes. If Oumuamua was indeed a flat, shiny object capable of surviving the intense spin without snapping in half, it suggests a material strength that rivals our best artificial alloys. The chiromancy of stars. A contemplation. Why is finding pure metal so strange it comes back to the concept of probability? The universe produces elements in very specific ratios. For every 1 atom of gold, the universe makes millions of atoms of hydrogen. For every chunk of iron, there are mountains of silicon and clouds of oxygen. To find a pure material is statistically almost impossible in a natural setting. If you walked along a beach, which is a natural environment, you expect to find sand, silicon water and broken shells calcium. These are the materials of the environment mixed together by the waves. If you walked along that same beach and found a pristine shiny square block of titanium, you would not assume the ocean made it. You would not assume the wind carved it. You would assume someone dropped it. You would assume it was manufactured. This is the core of the alchemy argument regarding Oumuamua. The universe is a master alchemist turning hydrogen into heavy elements. But the universe is a sloppy alchemist. It leaves its workspace messy. It mixes everything together in giant clouds of dust. Civilization, whether human or alien, is a precise alchemist. We purify, we separate. We take the messy ore and smelt it, refine it, and turn it into a clean sheet of metal. We create order out of chaos. The data from Oumuamua was limited. We did not get a perfect physical sample, but the data we did get, the lack of dust, the high reflectiveness, the structural strength required to hold its shape, hints at a level of purity or refinement that makes the natural explanation difficult to accept without reservations. The contrast. The dirty snowball versus the silent ship. To truly visualize the strangeness of this event, we must use our imagination to paint two contrasting pictures. This helps us feel the weight of the two competing theories. The natural view. The dirty snowball, imagine a piece of a glacier torn from a frozen moon. It is not clear and beautiful, it is old and ugly. It has been travelling through the dark for 1 billion years. It is covered in cosmic soot and dust, making it look like a lump of charcoal. It is lumpy, pitted and irregular. As it tumbles through the dark, it is dead and silent. It is just a piece of debris, a leftover brick from when a star was building its planets. It has no purpose, its arm is just falling through the void. When the sunlight hits it, it warms up slightly, perhaps venting a little bit of gas, but mostly it's just a rock obeying gravity blind and dumb. The artificial view, the stainless steel traveller. Now imagine something else. Imagine a surface that is not rock but metal. It is incredibly thin, perhaps only 1 millimeter thick but wide like the sail of a giant ship. It is ancient. Micrometeoroids, tiny dust grains moving at bullet speeds, have scratched it over the eons, giving it a reddish tint. But underneath that dust, it is not a chaotic mix of ore. It is a refined lattice of atoms. It is colder than anything on Earth. As this object enters the solar system, it doesn't tumble like a clumsy rock. It spins with a rhythm. It catches the light of our sun. Because it is metal, it acts like a mirror. It reflects the starlight. It captures the pressure of the light itself, the photons bouncing off its surface, using that tiny push to steer, to accelerate, to move away from the gravity that tries to trap it. The difference is in the order. The dirty snowball represents chaos. The random clumping of leftover dust and ice. The metal ship represents intent. The arrangement of atoms into a specific structure to perform a specific function. We are left with a haunting question: was Oumuamua a piece of the universe's trash, a jagged rock tumbling in the dark, or was it a product of refined alchemy, a manufactured alloy sent across the stars, reflecting our sun's light off its cold artificial skin? The spectrum told us it was red, the spin told us it was strong, the speed told us it was pushed. The combination tells us that we might have been looking at the first piece of stainless steel drifting in the cosmic ocean. When the object we call 3I, later named Atlas, entered our solar system, humanity did what we have always done when faced with the unknown: we listened. From the moment the Pan-STARRS telescope identified the anomaly radio telescopes around the world swiveled in unison, the great ear of humanity. The massive dishes of the Deep Space Network in California, Spain and Australia, along with the Green Bank telescope in West Virginia, turned their giant white bowls toward the point in the sky where Atlas was moving. We were expecting a greeting. Our science fiction had prepared us for a sequence of prime numbers, a pulsed radio beat, or perhaps a stream of binary code that would unfold into a picture of a hydrogen atom. We were ready for the first contact scenario where the aliens introduced themselves. Instead, we got the Great Silence. For weeks, as Atlas accelerated past the sun and began its loop back out toward the dark, our most sensitive machines picked up absolutely nothing. There were no radio waves, there were no laser pulses, there was no radar ping. In the electromagnetic spectrum, Atlas was as dead as a stone. This silence was more confusing to our scientists than the object's speed. If you build a ship capable of travelling between stars, surely you build a radio to call home. If you are an explorer, surely you want to announce your arrival. The lack of a signal forced us to confront a difficult question. Why would an advanced traveller remain silent? The energy of conversation. To understand the silence, we must first understand the cost of speaking in space. For us, sending a text message or a radio broadcast is cheap, but in the vast distances between stars, communication requires immense amounts of energy. To send a signal from one star system to another, across light years of empty void, you have to shout very, very loud. You have to focus a beam of energy so tight and so powerful that it can survive the journey without fading into the background static of the universe. Perhaps Atlas did not signal, because it was conserving energy. We know the object accelerated using the gravity of the sun, a maneuver that cost no fuel. This suggests a design philosophy of extreme efficiency. If Atlas is an automated probe running on batteries or a decaying power source that has lasted for millions of years, wasting energy on a hello might be seen as a design flaw. Every joule of energy used to transmit a radio wave is a joule of energy that cannot be used for navigation, heating, or thinking. In this view, silence is not an act of hostility, it is an act of survival, the concept of cosmic stealth. However, there is a more fascinating and perhaps slightly unsettling possibility. This brings us to the concept of stealth in the universe. On Earth, stealth technology is used to hide planes from radar. We shape them with flat angular panels to deflect waves, and we paint them in materials that absorb heat. Atlas had a strange shape, flat pancake-like and extremely thin. While this shape was perfect for catching the light of stars to push it forward, it also happened to be an ideal shape for deflecting radar. But why hide? There is a theory in astrobiology and science fiction often called the dark forest hypothesis. Usually this theory is told as a ghost story. It suggests that the universe is a dark forest full of silent hunters, predators, and the reason we don't hear aliens is that the smart ones stay quiet to avoid being eaten. But let us look at this theory through a softer, less scary lens. Let's retell the dark forest not as a place of predators, but as a great library. Imagine the universe as a massive ancient library at night. It is vast, beautiful, and filled with knowledge. In a library you do not scream, you do not run around shouting your name, you walk softly, you observe, you respect the silence of others. If a civilization is old enough and wise enough to build a ship like Atlas, they might view the universe as a place of delicate balance. They might not be hiding from monsters, they might simply be practicing good manners. Noise is pollution. When we humans entered the radio age, we started blasting our television signals, our military radar and our radio songs out into space. We became the noisy child in the library. Atlas might come from a culture that values informational hygiene. They do not pollute the spectrum. They move through the dark like a canoe moving through a quiet lake, leaving no wake, making no sound, disturbing nothing. This gentle stealth suggests that Atlas was not a warship, but a ghost, a silent observer passing through our lives without touching them, the mirror of the humanity voyager and pioneer. To understand the silence of Atlas, we must look in the mirror. We must look at the times we tried to break the silence ourselves. In the 1970s, humanity launched the Pioneer and Voyager spacecraft. These were our first emissaries to the stars. Because we knew these machines would eventually leave the solar system and drift forever in the galaxy, we attached messages to them. Pioneer 10 and 11 carried gold anodized aluminum plaques. These plaques featured drawings of a human man and woman, a map of our solar system, and a diagram showing exactly where Earth is located relative to nearby pulsars, dying stars that act like lighthouses. Voyager 1 and 2 carried something even more ambitious, the Golden Record. This was a phonograph record containing sounds of earth, wind, thunder, birds, whales, and greetings in 55 languages. It had music from Mozart, Chuck Berry, and traditional songs from around the world. We sent these bottles into the cosmic ocean with a heart full of hope. We wanted to be found, we wanted to say we are here, we are music, we are math, we are alive. But looking back, there is a deep loneliness in those golden records. They are the desperate wave of a castaway on a desert island. We shouted because we felt alone. We shouted because we are a young civilization eager for validation. Now compare Voyager to Atlas. Voyager is a scream for attention, Atlas is a confident silence. If Atlas is a probe from a civilization that is 1 million years older than us, they may have outgrown the need to shout. They might have sent out their own golden records eons ago, and realized that nobody replies or that the conversation is meaningless across such vast timescales. Perhaps the creators of Atlas understand something we do not, that the true nature of an interstellar traveler is solitary. When you travel between stars, you are disconnected from your home by thousands of years. Even if Atlas had sent a signal back to its home star saying, "I found a blue planet with biological life," that message might take centuries to arrive. By the time the reply comes back, the civilization that built Atlas might be gone or changed beyond recognition. So Atlas does not talk, it simply watches. The Fermi paradox, where is everybody? The arrival of Atlas forces us to confront the Fermi paradox. Decades ago, the physicist Enrico Fermi looked at the math of the galaxy. There are billions of stars similar to our Sun. Many of them are billions of years older than our solar system. If even a tiny percentage of them have Earth-like planets, and even a tiny percentage of those developed intelligent life, the galaxy should be teeming with civilizations. They should be everywhere. So Fermi asked, where is everybody? Before Atlas, we had two main guesses. We are alone. Life is incredibly rare and we are the only ones here. They are dead. Civilizations destroy themselves with nuclear weapons or climate collapse before they can travel the stars. Atlas offers a third, more profound answer. They are here, but they are polite. The paradox exists only because we assume that aliens would act like us, loud, expansionist, and eager to colonize. We assume they would build Dyson spheres, giant shells around stars to harvest all energy that we could see from far away. We assume they would colonize every planet they see. But what if advanced intelligence evolves toward minimalism? Look at our own technology. Our computers used to be the size of rooms, now they fit in a pocket. Our engines are becoming more efficient. Maybe as a civilization advances, it uses less energy, not more. Maybe it becomes quieter, not louder. Atlas was small, only about 100 meters long. It was thin, it was unpowered, it was silent. It fits the profile of a sustainable galactic traveler. It doesn't burn forest to fuel its journey, it rides the gentle currents of starlight. If the galaxy is full of probes like Atlas, we wouldn't see them until they were right on top of us. The Fermi paradox isn't a paradox at all. It's just a failure of our listening devices. We are listening for explosions and rock concerts while the rest of the universe is whispering poetry. The ethics of observation. There is one final reason for the silence, one that speaks to the ethics of science. Imagine a human biologist studying a rare tribe of gorillas in the jungle, or a marine biologist studying whales. The golden rule of observation is do not interfere. If the biologist walks into the gorilla troop playing loud music and handing out candy, the behavior of the gorillas changes. The data becomes corrupted. To truly understand the subject, the observer must be invisible. If Atlas is a scientific probe, its mission might be to scan biological systems like Earth without contaminating them. If Atlas had started broadcasting radio signals at us, it would have changed our history. We would have panicked or worshipped it, or stopped our own development to just listen to it. By remaining silent, Atlas allowed us to continue being ourselves. It looked at us, collected its data on our nitrogen-oxygen atmosphere and our blue oceans, and moved on. This implies a moral code. It implies that the creators of Atlas view us not as enemies, and not as resources to be harvested, but as a protected nature reserve. Conclusion: the echo of silence. And so the object tumbled past Earth, spinning every 8 hours, reflecting the light of our sun, but offering no words. The silence of 3i Atlas was not an empty silence. It was a heavy silence. It was the silence of a parent watching a sleeping child. It was the silence of a monk in meditation. It reminded us that we are not the center of the universe. We are not the main characters in the galactic movie who deserve a dramatic speech from the aliens. We are perhaps just one more interesting data point in a catalogue that contains millions of other worlds. As Atlas faded from the view of our telescopes moving back into the cold darkness beyond the orbit of Saturn, it left us with a feeling of profound smallness. We shouted hello at the void. The void glanced at us, smiled silently, and kept walking. That silence was louder than any explosion. It told us that the universe is vast, ancient, and patient. And if we want to join the conversation, we might need to learn how to listen before we learn how to speak. The night sky is never truly dark, not for those who know how to look at it. While the rest of the world sleeps tucked away in the safety of their beds, a different kind of population wakes up. These are the Watchers. They are scattered across the globe, separated by oceans and languages, but united by a single obsessive purpose to catch the faintest whisper of light moving against the backdrop of eternity. For the professional astronomers, this is a job of extreme endurance and isolation. Imagine sitting atop a mountain in Hawaii, or in the dry high deserts of Chile. The air is thin there, making it hard to breathe if you move too fast. It is freezing cold because clear skies usually mean the heat escapes the Earth rapidly. Inside the control rooms of these massive observatories, it is not like the movies. There is no person looking through a glass lens with one eye. Instead, there are rows of monitors glowing with red light to protect night vision. There is the hum of cooling fans keeping the supercomputers from overheating. There is the endless taste of stale coffee. When the object first appeared, it was just an anomaly in the code. It was a string of numbers that did not make sense. A professional astronomer does not look at a picture and shout, "Eureka!" They look at a graph and say, "That is funny." This specific object was moving too fast. In the language of their trade, it had a high eccentricity. That means it was not moving in a nice round circle like the planets do around the sun. It was diving in, cutting a sharp line through the solar system and preparing to shoot back out. But the professionals were not the only ones watching. In backyards across the world, from the suburbs of London to the rural fields of Australia, the amateur community was alive. These are the people who spend their own money on expensive telescopes, who build observatories in their garden sheds. They are often the unsung heroes of astronomy. While the big government telescopes focus on specific tiny patches of the sky to study distant galaxies, the amateurs scan the whole sky. They are the alarm system. When the coordinates of this strange visitor were leaked onto internet forums, thousands of these backyard telescopes swung into position. It was a race. Every amateur wanted to be the one to capture a clear image to confirm the brightness to track the speed. The internet became a hive of activity. People were sharing data points, arguing about the trajectory, and comparing light curves. A light curve is simply a graph that shows how the brightness of an object changes over time. If an object is round like a ball, the light stays steady. If it is long and thin like a cigar, and it is tumbling end over end, the light gets bright, then dim, then bright again. The watchers saw the light dimming and brightening violently. The ratio was 10 to 1. That means at its brightest, it was 10 times more luminous than at its dimmest. This was shocking. Most asteroids are somewhat round like potatoes. To have a shape this extreme meant this object was something entirely new. It was long, thin, and tumbling through the dark. The data was pouring in not just from the billion-dollar facilities, but from retired engineers and high school teachers with telescopes in their driveways. They were all witnessing the same impossible dance. However, while the community of watchers was buzzing with excitement, there was a heavy, noticeable silence coming from the top. The major organizations NASA, the Jet Propulsion Laboratory, the European Space Agency were quiet. To the general public, this silence felt suspicious. In the age of instant information where we expect a tweet or a post the moment something happens, a delay of a few days feels like a conspiracy. People began to ask questions. Why haven't they released the high-resolution images? What do they know that they are not telling us? Is the government trying to hide the existence of aliens? The gap between discovery and announcement became a breeding ground for fear and wild theories. But the reality inside these organizations is often much more boring than a cover-up. It is the burden of accuracy. If a YouTuber makes a mistake and says the object is an alien ship, they get 1 million views. If NASA says it is an alien ship and they are wrong, they lose their funding, their credibility, and their reputation forever. There is a massive difference between scientific caution and hiding the truth. When the scientists at the Jet Propulsion Laboratory saw the data, they were likely just as excited as the amateurs, perhaps even more so. But they had to be sure. They had to check their math. They had to calibrate their sensors. They had to argue with their colleagues in meeting rooms, staring at whiteboards covered in equations asking, is there any other explanation? This process takes time. They have to rule out everything else first. Is it a glitch in the telescope gnome? Is it a piece of an old rocket booster? Num. Is it a comet releasing gas? Maybe. They have to run simulations calculating the gravitational pull of Jupiter, the Sun, and the Earth to see if those forces explain the movement. Only when they have eliminated every boring possibility can they step in front of a microphone and say, we have found something interesting. Yet that silence creates a vacuum and human psychology rushes to fill that vacuum. This brings us to the complex relationship between truth and hope. When we look up at that dark, endless sky, we are really looking into a mirror. What we think the object is says more about us than it does about the rock. For many, the idea that this visitor was artificial, a ship, a probe, a piece of technology, was a desperate hope. We live on a fragile planet. We are fighting amongst ourselves. We feel lonely in the universe. If it were an alien ship, it would mean we are not alone. It would mean that someone else survived their own technological adolescence and made it to the stars. It represents a savior, or at least a big brother. We want it to be aliens because we want someone to talk to. On the other hand, there is a deep primal fear. If it is a ship, are they friendly? History on Earth tells us that when a technologically advanced civilization meets a less advanced one, it usually does not end well for the less advanced group. If the object was a scout checking our defences or scanning our atmosphere, that is the stuff of nightmares. So the human mind oscillated back and forth. One day we hoped it was a message, the next day we prayed it was just a rock. The internet forums were a battleground of these emotions. People analysed the non-gravitational acceleration, a fancy term meaning the object sped up slightly without a clear push from gravity and used it as proof of engines. Others argued it was just frozen hydrogen boiling off the surface acting like a tiny natural thruster. We projected our dreams and our anxieties onto a blurry dot of light that was millions of kilometres away. But as the weeks went on, a strange sense of relaxation began to settle over the watchers and eventually the public. The object was leaving. Regardless of what it was, whether it was a shard of a destroyed planet, a weird comet, or a derelict alien buoy, it was not stopping. It had dropped into our solar system from the north, swooped around the sun, brushed past Earth, and was now heading back out into the deep black void. It did not enter into an orbit. It did not slow down to say hello. It did not fire any weapons. It just kept moving. There is a profound peace in the laws of physics. They are consistent. They do not care about human politics or fears. The astronomers calculated the trajectory with extreme precision. They knew exactly where it would be in 1 month, in 1 year, and in 100 years. It was on a hyperbolic path, which means it had enough energy to escape the sun's gravity forever. It was heading toward the constellation of Pegasus. The tension that had gripped the world began to fade. The news cycles moved on to other stories. The conspiracy theories lost their steam because nothing happened. There was no invasion, no landing on the White House lawn, just a silent passage. For the watchers in the dark, the amateur astronomers in their backyards, there was a bittersweet feeling. They watched the dot get fainter and fainter. Every night it was a little harder to find. It became a magnitude 24 object, then magnitude 25, visible only to the most powerful eyes on the planet like the Hubble Space Telescope. Finally it was gone. It slipped beyond the reach of our senses, returning to the interstellar darkness from which it came. It became a ghost. The realization that settled in was one of smallness, but also full of safety. We are tiny specks in a vast universe. Things will fly past us. Some will be rocks, some might be ice, and perhaps one day some might be machines. But for now, the universe was simply behaving as it always has. The planets kept spinning, the sun kept burning. The visitor obeyed the laws of motion just like everything else. The watchers packed up their telescopes. They covered the lenses, turned off the cooling fans, and went back inside to their warm houses. They drank their coffee and went to sleep knowing that the sky was empty again, and that there was a comfort in that emptiness. The mystery remained, but the danger had passed. The silence of the organizations wasn't a cover-up. It was just the slow, methodical ticking of the scientific clock, and the object, whatever it was now just a memory drifting silently into the forever, taking its secrets with it, leaving us alone once more to wonder what else is out there in the dark. As the final days of the year approach, we stand at a quiet turning point. The excitement of the discovery has settled into a steady, sudden observation. We are now watching the long goodbye. Throughout the month of November, the object known as 3I Atlas will begin to dim significantly. It is moving away from the heat that made it wake up and shine. The sun, once a blazing fire close to its face, is becoming smaller and more distant with every passing hour. By December, the bright tail that fascinated astronomers will likely fade away. The ice that was melting to create that beautiful stream of gas and dust will freeze solid again. To the eyes of amateur stargazers using backyard telescopes, Atlas will vanish into the black background of space. Only the largest and most powerful observatories on Earth will be able to track it. It will look like a faint spark, a tiny ghost drifting into the dark. Looking a little further ahead, the journey of this traveller has one more dramatic event in our neighbourhood. In the year 2026, calculations predict that 3i Atlas will cross paths with Jupiter. This is not a collision, but a meeting. Jupiter is the king of planets, a massive giant made of swirling gas and storms. Its gravity is incredibly strong. As Atlas approaches this giant, it will experience a gravitational kick. Imagine a child running past a spinning merry-go-round and grabbing the handrail to swing themselves faster. This is what will happen. Jupiter's gravity will grab hold of the tiny traveller and sling it outward. This encounter will change the speed and the angle of Atlas. It will act as the final push, launching the object out of our solar system forever. After 2026, the speed of the object will increase to tens of thousands of kilometers per hour, rushing towards the interstellar exit door. Now let us pause the science for a moment. Let us step away from the mathematics of orbits and gravity. Let us try a gentle thought experiment. Let us imagine the what if. What if 3i Atlas was not just a rock and ice? What if the conspiracy theorists and the dreamers were right? What if deep inside that frozen shell there was a window? What if it was a ship carrying a silent crew from a distant star? If there were eyes watching from that window as they passed us, what would they have seen? They would have seen a miracle in the void. They would have seen an Earth. From their vantage point, our planet would look like a precious gemstone hanging in nothingness. They would see the vast deep blue of our oceans, which cover 70% of our surface. They would see the swirling white clouds that bring us rain and shade. They would see the browns and greens of the continents where we live our lives. But more importantly, they would see our fragility. From out there, you cannot see borders. You cannot see the lines on a map that separate countries. You cannot see wars or politics or money. You only see one single system. They would see the atmosphere, that thin, blue line that hugs the curve of the planet. It looks thinner than the skin of an apple, yet it is the only thing shielding all known life from the freezing vacuum of space. If they were listening, they might have heard our radio waves, a chaotic noise of music news, arguments and laughter. They might have wondered about the creatures living on that blue marble. They would see a planet that is teeming with life, vibrant and warm in a universe that is mostly cold and dead. They would see how lonely we are floating there by ourselves. And perhaps they would feel a sense of sadness as they sailed past, unable to stop watching the beautiful blue light fade into a tiny star behind them. But that is just a dream. The reality is that 3i Atlas is likely returning to its natural state, a frozen relic of the early universe. As the years turn into decades, Atlas will cross the invisible boundaries of our home. It will pass the orbit of Neptune, the windy blue giant. It will drift through the Kuiper Belt, a ring of icy rocks that act as the debris of our solar system's creation. Finally, it will enter the Oort cloud, the vast dark shell that surrounds us. The light of the sun will become no brighter than any other star in the sky. The temperature will drop to near absolute zero, hundreds of degrees below freezing. The silence will be total. There is no wind, no sound, no movement other than the steady drift forward. It is returning to the eternal darkness from which it came. However, here on Earth, things are different now. 3i Atlas has left, but it has left a mark on us. Before this arrival, many people looked at the night sky and saw only a flat wallpaper of twinkling lights. Now we see depth. We understand that the universe is not just a static picture. It is a busy highway. Objects move, travel, visit, and leave. We have realized that our solar system is not a fortress with closed gates. It is an open garden, and sometimes strangers walk through. We have collected data that will keep scientists busy for generations. We have analysed the light reflecting off its surface to understand what it is made of. We have measured its path to understand gravity better. But beyond the science, we have gained a new perspective. We looked up together. For a few months, humanity shared a common curiosity. We were reminded that we are all standing on the same small rock looking out at the same giant mystery. The story of 3i Atlas ends not with a bang, but with a quiet fade. It is like a guest who stayed for a short dinner and then walked out into the snowy night. We close the door, but we remember the conversation. We check the locks, but we keep looking out the window. And so we send a final thought into the dark. Rest well, traveller of the void. The road ahead of you is long and empty. You have millions of years of silence ahead. May your ice remain cold and your path remain true. You carried the dust of distant stars to our doorstep, and now you carry our gaze back out into the deep. Drift on through the black oceans of time, past the sleeping nebulas and the burning stars. We will remember that you were here. We will keep watching the sky, waiting for the next visitor to wander in from the night. Goodbye, Atlas. Sleep well in the endless dark.